take a region in the xy plane, so an area in the xy plane, and rotate it about a line, right? If we rotate a shape, right, in a two-dimensional plane, if we're rotating it now, making it three-dimensional, we're going to create a solid. So over here on the left, we can see that we are rotating this around the x-axis, so we have that kind of 3D shape below it. And then over here, we are rotating around the line. It looks like we're rotating around the y-axis, right? So we create a solid that's got a hole in the middle, right? So we're going to be finding the volume of these kind of things. So to find the volume of these kind of solids, we can think of slicing up the solid into multiple parts and then finding the volume of each piece. So, and then we can find the total volume by adding all of them up. Just going to move my calculator a little over, get it out of the way. Okay. So I'm just going to draw kind of a random curve here. So say we are going from A to B here on the x-axis, and let's just rotate around the x-axis here. So I'm going to do my best to kind of reflect this graph. So if I'm rotating this, kind of creating this little three-dimensional shape here. Right? If I wanted to find the area of the volume of this, we're just going to slice this up into different sections. So what we can do is think about, right, taking a section like this, right, technically there's one over here too. So if we slice it up, we're going to slice it into discs. Please ignore how bad my three-dimensional drawing is, right? So if we're just taking different slices of this, we are taking different discs throughout this thing. We can find the volume of a disc fairly easily. Right, the volume of a disc is just the area of the base, so in this case it would be pi r squared, right, where our radius is right here, times the height. And the height in this case, since we are along the x-axis here, right, this would be a delta x. So we would get pi r squared times delta x. And if we're thinking about this in terms of a function, right, if we let this graph up here that we rotated be f of x, our volume then becomes, for one disk, becomes pi, and then the radius here, right, would just be the height of the function. So we would say f of x squared, and then times delta x. Now, as we let these disks get thinner and thinner, so as we take more and more slices along this A to B interval, right, that delta x is getting much, much smaller. So as we let delta x get smaller, so in other words, as delta x, that was supposed to be an A, not a delta, right, so as delta x approaches 0, the total volume would be the sum of all of these disks. So that's going to become the integral, whoops, that was weird, from A to B of pi times our function squared delta x, right? So we're basically just taking these circles and finding the volume, the area of each circle, and as we add up each of those circles, we're going to get the total volume of the solid. You can kind of think about it like if you put like a circular piece of paper down and then you keep layering more and more circles on it, like even though a piece of paper is so thin, right, eventually if you layer enough circle pieces, right, you get a solid cylinder. So we're going to apply that same sort of idea here. So some helpful hints for finding volume is you always want to have a graph. It doesn't have to be a great, super accurate graph, but you want to sketch a graph and then draw what we call a representative rectangle. So that's basically just drawing a line or a little rectangle to show what's going to be rotated to help you find the radius. And you always want to remember that these representative rectangles, these slices, are always perpendicular to the axis of revolution. So that means if you're going to rotate around a horizontal line like the x-axis, you're going to end up with a dx integral. But if you rotate around a vertical line like the y-axis, you are going to use a dy integral. So we're going to do some problems. So the first problem we're going to do no calculator. We're going to find the exact volume of the solid form by revolving the region bounded by the graphs of y equaling 9 minus x squared, y equaling 0, and x equaling 0. So that's the x and the y axis. So I'm just going to draw a little graph real fast. Okay. So if I factor this real fast, that factors to 3 minus x and 3 plus x. So that means my x-intercepts are 3 and negative 3. So 1, 2, 3. So I know I'm going to hit the graph there. And then my y-intercept is 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. If I plug in 1, I get 9 minus 1 is 8. If I plug in 2, 9 minus 4 is 5. So 1, 2, 3, 4, 5. All right, so we have a little quarter of a parabola here. So we got y equaling 0 and x equaling 0, and then we want to find the volume by rotating the area bounded between them. So we are rotating this area, and we are rotating it about the x-axis. So I first need to visualize my slices. So like I'm going to draw a little rectangle here, and I'm going to visualize just if I revolve that rectangle. So this is going to be my radius, and my radius is the height of the function in this case, which is going to be 9 minus x squared. So if I want to find the volume of that solid, I'm going to pull the pi to the front, and since my rectangle is vertical, I'm going to have a dx integral. So my x limits are going to be from 0 to 3. My radius is 9 minus x squared, and I'm going to square my radius, and then I have a dx. So I'm just going to quick square that out. So it's going to be 81 minus 18 x squared plus x to the 4th. So then I'm going to get pi times 81x minus 6x cubed plus 1/5 x to the 5th. Evaluated from 0 to 3. So all of the zeros are going to cancel out. So then 81 times 3 is 243. 3 cubed is 27. And then 1/5 of 3 to the 5th. That is 9 times 9 times 3. So that's also going to be 243. So then 243 plus 243, that's going to be 486. Let's see, 6 times 27, it's 42, carry the 4, 2 times 6 is 12, okay, plus minus 162, plus, oh, hang on, that's not right, 243, and that's plus 1/5 of 243, there we go. Okay, so let's see. I got 243 minus 162. Okay, that's going to be 81. And then I'm going to make that a fraction over 5. That's 405. Plus 243 over 5. So that is going to be, what, 648 pi all over 5. So now let's go ahead and do one around the y-axis. So we're going to, again, exact area, so no calculator. We're going to do the graphs of, let's see, we got x squared, y equaling 4, and x equaling 0 about the y-axis. Okay, so x squared, so I got 1, 2, 1, 2, 3, 4. Then I got y equaling 4, so that's going to be right here. And then x equaling 0 is the is the y-axis, so I'm going to be revolving this area. We're going around the y-axis here. So in this case, my little representative rectangle, remember it's always perpendicular to the axis of revolution. So I want to know what my radius is going to be here. So I'm going to be having a dy integral, which means I need to change that function to be in terms of y. So this is the same thing, right? This is really that x equals the square root of y. So that's going to be my radius value, because it's just the difference between the 0 line and that function. So my volume is going to be pi. And now I'm doing a dy integral, so I'm going to use the y limits. So that's going to be 0 to 4. Because I start down here at 0, we end up here at 4. My radius is the square root of y. So radius squared dy. So that's going to be pi integral from 0 to 4 of y dy. Right, so this one is nice and easy. So this is going to be pi over 2y squared, evaluated from 0 to 4. So the 0 term would cancel out, so this is going to be pi over 2 times 16. So we're going to get our volume here is 8 pi. So now let's try a couple with a calculator, and it's going to be slightly different. So in this one, we want to find the exact volume of the solid form when the region bounded by y equaling x squared and y equaling 4x minus x squared is rotated around the line y equaling 6. Okay, so let's go ahead and actually use the graphing calculator to do this. So let's go to y equals. See, I have x squared here, 4x minus x squared, and then y equaling 6. I'm just going to go ahead and graph that too. Go ahead and graph that. Okay, so we have this little graph here. Okay, I'm going to go ahead and zoom my window in a little bit. So let's see, let's maybe go from -1 out to 6. Let's go from -1 to 8. Let's just get a little closer here. Okay, so I'm just going to quick kind of sketch a picture. Okay, so we have, that's our red graph there. And then we got the line y equaling 6. Okay, so we are revolving this region around this line. So if we think about it, there's going to be a hole inside of this solid. So it's going to look a lot like, if I scroll back to the beginning with those pictures, it's going to look a lot like this one on the right, because there's a gap between the area that we're rotating and the axis of revolution. So it's going to be like you create a vase. There's going to be a space in the middle. Okay, so in this case, we have to kind of think of two volumes. So the first thing I want to do is I want to go from my axis of revolution. I'm going to go as far as I can. So I'm going to call this my big radius. It's my outer radius. So that line is the distance between the two functions, so I'm going to subtract them. So my top function is 6, and that bottom function is x squared. So if I was just rotating that and I didn't want a hole in the middle, right, if I was rotating this whole region here, then I would just have that as my volume. But now, if I was just rotating the top function here, I'm going to call this little r for my inner radius. Right? If I was just rotating that inner function, that would be my top function would be 6, and my bottom function would be the 4x squared. I'm sorry, the 4x minus x squared. So if I was just rotating that top function, right, I would have this solid would be created. So I basically want to take out that inner piece. I don't want that inner piece to be there. So my volume, we call this the washer method because a washer is like a metal ring with a hole in the middle. To find our volume right now, we do our outer radius squared minus our inner radius squared. So what we essentially do is we find the outer volume and we subtract the inner volume. So that way we can take out the hole. So we need to know what our a and b terms are. So because we are rotating around a horizontal line, we're going to have a dx integral here. And then we can see that, I'm going to hit trace here, I hit 2, right? Our curves intersect at 2. This is the point 2, 4 here. Right, and then they intersect at 0, 0 here as well. So we are going to integrate, in this case, from 0 to 4. Our outer radius is going to be 6 minus x squared, and then we're going to square that, minus our inner radius. Now, we still want to find our exact volume. So to do that with a calculator, we're going to go back to our home screen. We're just not going to put the pi in. We'll multiply the pi in manually at the end. So we're going to go to Math, option 9 for our integral. We got our limits from 0 to 4. And now you want to be careful. So we're going to type in our outer radius first. And I'm going to square that. And then I'm going to subtract. You want to be really careful with these parentheses here. Subtract our inner one. We definitely want to make sure we have all the parentheses. That's why we want to write it out super carefully. That way you can kind of check it. And then for exact, I probably want it to be a fraction. So I'm just going to make it a fraction automatically. So I'm going to get pi times 128 over 3, right? Or just 128 pi over 3. So let's do another washer one just so we can kind of get the idea here. So let's do around a vertical line now. So we want to find the exact volume of the solid form in the region bounded by y equaling x squared minus 4, y equals the square root of x plus 2, and y equaling 0 is rotated along the line x equaling negative 4. Okay, so let's clear this up a little bit. Oops, clear. Okay, so we've got x squared minus 4. We have the square root of x plus 2 and y equaling 0. So that's just the x-axis. And then I want to go around x equaling negative 4, so I definitely want to make sure that that is in my window. And then I don't know how far up we need to go, so let's see the graph first. Okay, you know what? I am going to graph the line y equaling 0 just so we have it in a different color. Which means I need to change the color. Okay. Oh, and we'll make it pink. Oh, I didn't actually change the color. Okay. Enter. Magenta. Okay. Graph that again. There we go. Okay. Okay, so it looks like they intersect. We got to find where that intersection point is, but they start at negative 2, 0. Okay, so I want to go around 1, 2, 3, 4. So my axis of revolution is right here. They intersect at 2, 0. And then let's see where that second intersection point is. So second 5, we're going to scroll over towards that intersection point. There we go. So it looks like at 2.473. I'm going to go ahead and save that as my B value. Okay, go back to the graph. Okay. And then let's see, we got 2, 0. I know that this is going to be 1, 2, 3, 4. If I plug in 3, that's at 5, 1, 2, 3, 4, 5. Okay. And then I've got that. That's a little bit between 1 and 2 there, and our intersection point is around at 2. Okay, so we're like here. And we just want to take this volume, this area, and rotate it around the reflection line, the revolution line rather. So I always like to kind of think of that inner and outer. So you always want to start on your axis of revolution and draw to the furthest point. Okay, so my furthest point takes me to the parabola curve. So the first thing I actually want to do is change my functions to be in terms of y, so x equals functions, because we are going to have a dy integral, right? This is a vertical line, so we're going to have a dy integral here. So that's going to be y plus 4 equals x squared. So I'm going to take the square root of y plus 4, and then I just want to make sure I have the positive values here. So my outer radius is only ever touching this section, and that's where my x values are positive, so I am going to have the positive square root here instead of the negative. Sometimes you do need both of them, so that's just something to look out for in case you're solving a problem. And then y equaling the square root of x plus 2, I would square that both sides. Right, so this is y squared minus 2 is equal to x. Okay, so then we have, right, so our outer radius, our large radius is going to be, it's the distance from the function to the line. So this distance right here is a distance of 4, right, into our function. You can also think about it doing like right minus left, right? It's the right function minus the left function. So our right function is that square root of y plus 4, and then we're going to subtract the negative 4 on the left, right, from that, this is line x equaling negative 4. So we're going to get the square root of y plus 4, all plus 4 as our outer radius. And then our inner radius, if I go, just going to erase this distance here so I have some space, right, our inner radius is from here to here. So that is the distance between the y squared minus 2 and the line negative 4. So I'm going to do y squared minus 2 minus negative 4. So that's going to be y squared minus 2 plus 4. So we get that our little radius here, our inner radius, is y squared plus 2. So then our volume is going to be pi times the integral. So we are looking at y coordinate of 0. And then I actually just realized that we don't want to store the x coordinate as our b value. I need the y coordinate. So I'm going to do the y coordinate at b, and I'm actually going to restore this as b. We want the y coordinates. So they intersect at 2.473, comma 2.115. So we're going to do 2.115, and then it's our outer radius, so the square root of y plus 4 squared minus the inner radius squared, and then dy. So again, I am going to go up, and then we actually are probably not going to be able to get an exact volume here. Okay, so we are going to go, I'm going to finish storing that, there we go. And then math 9, we're going from 0 to what I just stored as b. My outer radius, square root, I'm just going to use x's instead of y's here just because that's my variable key. Make sure I get out of that square root. Close that first parenthesis and square my outer radius, and then subtract, in this case, x squared instead of y, just because that's my key. Close that parenthesis, square it, dx. I'm going to see if it'll give me an exact answer. I don't think it will. Nope. And then we'll just multiply that by pi. All right, so that equals 52.979 pi, which is approximately 166.439 units cubed, if you were talking about volume.